just a bit of context. So I'm going to be redoing the comprehensive example from homework 5. And I'm doing a homework 6 version of it. And first thing is I'm going to show you the differences between the two. So I already implemented both of them out, and then I ran it through a diff checker. And then after this, we'll get into the code and do it line by line. Alright, so I ran a diff checker through the homework 5 version and homework 6 version. The only difference is that we have our build up here, and we had to explicitly set some local variables to 0 since we don't have access to .fill anymore because we're not using labels. Other than that, everything's the exact same except we changed our label names to R5 offsets. We changed our LDs to LDRs and our STs to SDRs. And that's the only difference throughout the entire program. All the way to the bottom. Yep. And then, of course, instead of storing this value into some arbitrary label, we return the value. We store it R5 offset 3, and then we also have a teardown. Yeah, other than that, it's the exact same. Alright, so I'm going to show you guys how to do a homework 6 example. And I'm using the same example I did for the homework 5 video. I just wrapped it in a function, just so you guys can see how similar it is, because really the only difference between homework 5 and homework 6 is that instead of using labels to store your arguments and your local variables, we're going to use R5 offsets for your arguments and local variables. And I guess there's one thing you also need to know is you need to know how to call a function. And we're going to do a quick example of that right there. Because this is really the only thing new you got to be learning. And for the inside the Callee part, you just got to rewire your brain to use these offsets instead of labels. So, anyway, to continue, we'll just start with these lines of code. These two, they've been done with us, for us with assembler directives. But this one needs to be done using instruction, so because we need to call a function. This line of code. So we gotta follow the calling convention. Basically, if this is our stack, we need to put two things on that stack. We need to put our arguments there. We're going to use str commands for this. And then we can call JSR on our function, and our return value of JSR, whatever we JSR to, the return value is going to be magically top of stack for us to use. So, but right now our stack looks like this. How can we get to that state? Well, first thing we can do is our stack pointer is right there. So to add two things, we can really just move this pointer up twice, which conceptually makes these two boxes for us. Do that with add R6 minus 2. That just moves it up twice. So now our pointer is pointing up here. Next thing to do is load our string. They're going to be stored as addresses in assembly. And we're going to use an str command. So R0 right now will have our address of the string. You can think of it as having S. We're going to want to put that right in the top of our stack. So the top of the stack is always going to be R6 offset 0. Use an str command. And R6 offset 0. And offset 0 just means store it directly at the arrow. After that line of code, we'll have our S in our register. Next thing we gotta do is we need to go length. So load R0 with length. Basically has length in R0 now. And we want to store that right there. And so what we can do is we can just use handy offsets parameter in our str command. We can just add offset of 1, which is going to store it at the arrow, but it's going to go +1, so right below is S. Let's going to put length right there. And then that's done. We've pushed our arguments. Now all we got to do is we need to call our subroutine. And your subroutines are really just labels that happen to have code right below it that follows the calling convention, so it kind of behaves like a subroutine. But it's really just a label, like a while label or a for label. It just happens to have build up and tear down code right below it that makes it act like a subroutine. So we'll just JSR that label, and we can assume that magically pushes our answer, basically our return value of our function we just called, right at the top of the stack. And so we want to grab that into a register because it's pretty important to us. And one thing it also does is it'll also make sure once you call JSR, the stack pointer will be moved up to point to that return value. So we'll LDR R0 R6 offset 0, and that gets our return value into a register 0. Should probably name this R0 earlier, but yeah, it's register 0. And then that's it. So now we have our ret val and register. Now before we do anything, we need to clean up after ourselves. So this is how the stack looked like before we did our mess, right? But we kind of put a bunch of a residue now on the stack that we don't need anymore. And so we want to clean up after ourselves, we don't want to litter. And so how can we do that? We can basically pop all this stuff off just by moving the pointer down by 3 back to this where it started. So we can do that with just add R6 R6 with +3. And now we've cleaned up after ourselves, and the stack basically looks just like how we left it. So now we have a ret value. We have in our register 0 that we call the function to get. And so now we'll store that R0 at our result table. So that's an example of how you can call a function. Right, so now we're going to go into the Callee perspective. And so to be a Callee perspective, the first thing you're going to do is copy paste your build and tear down code. What I'm going to do is below this, I'm going to make a label called text string to int. This might be provided to you in your homework. I'm just going to straight up copy paste build and tear down code. I'm going to bring my pseudocode a little lower so I can read it now. Copy paste this stuff. Move it right there. It tends to be useful to have your pseudocode side by side. If you want that might help. But anyways, we'll start with this. And it says we have to set x to -4 minus num LVs. So how do I count the local variables? Well, I just look for all the definitions that I made inside the function body. So here we define a variable value, so that's 1. Here we define a variable I. Here we define a variable left shifts. Here we define card digit. Here we define digit. So it looks like we have 5. So I'll set that to -9. And it looks like we're done with that. And now before we ever start the subroutine body, we're going to do a little bit of preparation work that makes our life a lot easier. And so what we did was we just set this this value to -9. And what that did was that made 5 spots for us at these spot locations. R5 is 2. So, and we're just following this formula here. I'll leave that below. The third local variable, R5 is 2. We also made a 4th and a 5th one right here. So that's what we did. That's really all we did by just setting this to -9. Made some spots for us. So name this 4th and 5th. And so what we have to do now is we have to give them names. So I'm just going to name it from top down. So I'll name this one value. Name this I. This left shifts. This card digit. This digit. And after we give it these aliases, we can really just treat them just like labels. So now instead of using something like LD value, like we would in homework 5, or LDR0 value, we can just, instead of using LD commands, use the LDR command. And we'll just replace this value with this R5 offset 0. You can really treat them just like labels. And the nice thing is you can also do this for your arguments as well. So I'm using this formula down here, ith argument. The first argument is R5 offset 4. And it looks like it's hex string for us. Hex string. And the next argument is called len. So these you don't really have a choice to name because they're given to us by the function, but it's nice to have a name so you can just start looking at your table and you don't have to like scroll up and down and keep counting. And then once you do this naming, then you're ready to start implementing your subroutine body. Right? So we just really just go line by line. Maybe I'll even put this below the teardown, the build and teardown codes. I'll put that right there actually. So subroutine body, first line of code is int value equals 0. So in order to do that, we just get any register 0. And then we're going to store that into value. So it might be tempting to do str0 value, but this is homework 5. That's a homework 5 thing. In homework 6, we're using stack, and we got to use these offsets instead of these names. So I'll use str0 instead. Value, I'll copy paste its alias here. It's R5 offset alias, and that's really the only difference in homework 5 and homework 6. I have a for loop. I didn't prepare it. Let me go copy paste that real quick. Actually, I think it's over here. Nice. I have a for. So 4 right there. For loop initialization here. That's going to be int I equals 0. So same process above. And any register 0. And then I'm going to store that. Not an I, because that's not a thing anymore. We're going to use I's alias. Great. Next thing is prepare condition code. Looks like we need to get I minus len. So and it's just saying I minus len is 0. So get I minus len. And it might be tempting to do LDR0I like homework 5, but gotta use the aliases now. Then get length on another register. Alias. Length is a parameter, so it has a little bit different alias offset wise, but really you can treat them just the same. Local variables and arguments, they're very similar. You can treat them just the same. So, and then we're going to not R1, R1, add R1, R1, add them together. Now we have I minus len, so our condition code should be opposite of negative is 0 positive. It should be CP. So for body, int slash shifts 0. So you can get any registered 4. And then store. Okay, what? We named it offset 2. Great. That's already done. Right to that. So looks like a while loop now. Oh, it's supposed to be indented. Indenting doesn't really do anything in assembly, but it's for organization. It's really nice to do it. This while statement. So when I get a while statement, I'm gonna first go find the while template, just copy paste it. Pair condition code is going to be left shifts 0. LDR any register which is loaded with left shifts, and what will we name it? R5 2. And then we branch on what condition? I guess maybe it's better to not have this. So branch on opposite of positive is NZ. And while, so now we're done with that. And then we have a while body, which is plus equals value. I'm gonna actually try this. Let me copy paste this right there, so I can see it. Wall body is value plus equals value. So value is going to be, we decided to name R5 offset 0, so we'll load that R5 offset 0, then we'll add it with itself, that'll double it, we'll store it right back. Right, so that's it. Next line of code is left shift minus minus. So we'll load left shifts. What do we name it? 5 offset 2. Add it with -1. Store it right back. Perfect. Looks like that's it in our while loop, so we're done with that. Next we have int card equals hex string I. Int card digit equals hex string I. And so first thing is we need to get the right hand side so we can store it into the left hand side. So to get the right hand side into a register, we'll have to first get hex string's base address, which is one of our parameters. We'll load R0 with R5 4 right there. And then we need to add it with I. So I'm going to get another register with I, which we decided to put R5 offset 1. Add them together. Now I have the address of hex string of I, so I can load it into itself. You don't really have to load it into itself. You can load it in another register by just changing this first one. But we don't need hex string and we don't need I once we have the value hex string of I. So there's no reason to be keeping these R0 and R1 values anymore. So that's why I load it into itself, generally. So that's the right hand side. And now I just need to store that into car digit, which we decided was going to be R5 offset 3. str R0, R5 offset 3. It's done. And then int digit. This just initialize, or it just defines digit, doesn't do anything to it. But we've already kind of done that just by with this +9 that we did there, or with -9. We've kind of already allocated space for a digit in the stack, so we don't have to do anything with this line of code. Next thing is just an if-else statement. Go to my template. If-else. Right, that's not right there. And then so the pair condition code here, I just need to get car digit and subtract with -64. So I'll load R0, car digit, R5, 3. Great, so I'm just going to put a helper labeled on here, -64. Dot filled out -64. I don't have to worry about this -64, this value ever being treated like an instruction, because it's right below this ret command, and this ret will take us out of our this location entirely. If you wanted to be safe, I guess you could have tried like putting a halt here, but it's not necessary for now. So now load R1 with minus 64. I'll add them together. And this minus 64, you probably wondering, Max, you just said that we're not using labels anymore. This is just a helper label with a fixed value. You can kind of think of it like a constant that doesn't change. So it's not like a local variable or anything. Anyway, with that, so this actually finishes our condition. And greater than 64, opposite is less than or equal to. That's NZ. Alright, great. So if body, do this. How can I do that? Well, I need to get the right hand side and then store it into the left hand side. To get the right hand side is you take the char digit and store it at R5 OS 4 at digit str. Oh, I got subtract with 55 though, so make it helpful. Minus 55. 55. And I'll add them together. Then I'll store it at digit. So we got the right hand side, now we can just store it at the left hand side. Perfect. I think that's it. And then same thing with this bottom one here. Else body. Similar process. I'm gonna load digit in, or char digit in, sorry, because we need to get the right hand side. I'm going to load R1 with, we're putting in minus 48. I'm just gonna make a convenience label here. Minus 48. Add them together. We'll store it at. We want to store it at digit, which we decided was 4. Great, that finishes that. Okay, so we're at our else block. This is the end if part. This is one. Now our value plus equals digit. So in order to do value plus equals digit, we gotta get. Think of this as value equals value plus digit. We need to get the right hand side and store the left hand side. I'm going to do that. Let's first get value to one register. Value is an R5 offset 0. Great. And we need to get digit in another register, so we add them together. And add R0 and 1. And store it right into value. R5 offset 0. That's it. So done with that. I think that is reached the end of our for loop. We have to get this for loop update statement right there. I plus. We write this as I equals I plus 1. Just gotta get the right hand side so we can store it on the left hand side. So we'll do R0 of I. And then R1. Oh, we just need to get added by 1. Now we have I plus 1, and we store it at the left hand side, which is happen to be at the same offset, which copied R5 offset 1, or offset negative 1. Yep, that's done. Reached at this line code. And these two lines are our for loop closing brackets. And then we have something called return value. So notice that I have this return val spot comment. Looks like it's R5 offset 3. So what this means is that I just got to get value and store it in R5 offset 3, and then branch to teardown. After you return something, your function's basically over, and you should always branch to teardown. Otherwise, your function is going to keep going on when you don't want it to, right? Let's say I return something here, and I stored it at R5 offset 3, because I was reading a return comment. Looks like it's an else bracket. So let's say there's something like return char digit minus 48. That's basically what I did here. Now, if I just did only the storing and I didn't do the branch and teardown, my code's going to leak down and do some more lines of code when I didn't want it to. So that's why always a good habit is when you're returning something, it's returning value. We first gotta get value into register. Value is here. Then we're going to store it into R5 offset 3. And then we're going to branch the teardown. This is an important part to remember. Right now, it doesn't do anything. It's actually kind of redundant. But it's always a good habit to do this branch teardown. You want to really make it muscle memory to be branching a teardown when you return things. Right? It's one of the most common ways to completely mess up code. Many students have gotten like really bad time lab 3 scores, and the only thing they had wrong was this branch teardown they forgot. So just remember to do that. And that should actually be it. I think that's our whole function. And the process was almost exactly the same as homework 5. We just started using R5 offsets instead of labels, right? But it's basically the same video. And then we also had this. What was new to us is how to call functions, which was right here. These couple lines of code. But everything else really stays the same. So, all right. So I'm gonna run this through Complx. Code in real quick. Right. So. And I did add this little line of code here to load the stack as xf000. That's because Complx doesn't do that for you. It keeps this garbage data. So I just did that explicitly. But for the homework, you don't have to worry about this at all. It's just a small thing I had to do just to get Complx to work. But so after you run that command, notice R6 is xf000, which is the top stack. So now we can begin our caller code. Before we begin, I would like to make a new view. Small, and then let's go to the stack. So I'm just going to look at R6. I'm going to put exactly what I see in there. And now we're at the top of our stack. The first line of code is, like the one we're on right now, is I want to move the stack pointer up 2. So if this is the top of our stack, count up twice. These are the 2 spots we should be adding, and our stack pointer should now be pointing to EFFE. So if I press step, EFFE, so now my stack pointer is pointing right here to right here. Draw that. So it was pointing right there. After that line of code, now pointing right here to this value, 281 decimal, or aka that in hex. And now the next lines of code is we're loading R0 with string address. Notice R0 now has this value, which if I double click to change the hex, x4000, which is the address of our string. And you can find that. I'm going to click on view, go into code/data, and scroll down and see this is our string. So that's our address 4000. Now let's watch what happens. Now our pointer is here. This next line of code is storing that x4000 right on top of this arrow because the offset is 0. So this 281 is going to be overridden by x4000. Great. So that's one of our arguments on the stack already. Now we need to store our length right below that. We're just going to load length into R0 right there. And then we're going to store it right below this arrow. That's what this +1 is doing. It's instead of doing it directly with the arrow, directly at the head of the stack, it's going offset 1 below that and do it right there. So knowing that, press step, these 4. So now our arguments are pushed on the stack. Remember, the stack started out on this -43. We pushed 2 things on it, and now we store our arguments on there. Now this line of code is a JSR command. But as the caller, alright, we're going to treat this as a black box. Instead of pressing step, I'm just going to press the next line, which is basically just going to run this entire JSR command and as if it was one instruction instead of like actually going into the body. Kind of like a normal debugger. So all I should expect is that once I run this JSR hex string int, magically, right above my arguments, the return value should just pop in there. This should be pushed on the stack. So, and watch the stack pointer too. So it's right now it's pointing to my argument. But after I run this, I should expect something to magically be right on top of that. So I click next line, and look, right there. Your R6 is just moved up by 1, so it's no longer here. Pointing there. And all of a sudden, what's in there is the actual return value. And that's really it. So the rest of it you treat like a black box. So I'm just going to grab that return value, and I'm going to place it into R0. And now it's right there. I'll turn that into an integer. Perfect. So, then now we have to clean up after ourselves. So remember, if we started this program, our stack was pointing right there. So after we did all of our dirty work, we want it to be just back where it started. And we don't want to leave any residue, right? So that's why we have to add this R6, R6, offset 3. Watch your stack pointer, click step. We're back at XF1000. Right there. And just like that, you've successfully called the function. And so that's pretty cool. And then now it's just step forward, we get return results. Or like you got a result label. You store it at X789A and results. Now if you wanted to actually debug your subroutine and go line by line, step by step, instead of pressing next line, here you'd kind of just press step. It would take you into your subroutine. And you'll do all this stack build-up code and all your interior instructions and stuff. So this might help you to debug. And if you put a breakpoint, so let's rewind. Let's just say this while loop has been very problematic for me. So what I'm going to do is I'm just going to right-click on this. I'm going to mark this as a breakpoint. So now when you run this entire function, so I click on run, instead of running the whole program, it's going to run up until it hits the breakpoint, just like a normal debugger. And so I can turn that off like here, and then when I press run, to continue to the rest of the program all the way to halt. So yeah, that's really how we can use Complx. Hope to prove that this is working. And we can really call anything we want. So let's change our string up a little bit. Alright, so right now we have 789A. Let's change this to 589A. And so go to our program, we run it. Since our function, we've passed in our string address to our function, it shouldn't matter. We should get 589A or 22,682. We really change anything we want. We can change our length parameter. That's kind of scary to change our length parameter, but let's try this. Let's add an extra character. Actually, no, it's gonna overflow. Yeah, it's gonna overflow. Let's change the length to 3. Let's do that. So let's move our null terminator over here. And in our argument, let's change length to 3. Okay. And if we run it, I should expect a much smaller number. Yep. 589. We're missing the A. And maybe let's actually move our start array address. So we're passing in the address x4000. Let's actually omit this first character and leave was it 65, I believe? No. I think it was. There's something like that. And instead of passing 4000 to our function, let's pass 4001. Okay, and that's going to mean that the function thinks the string is starting over here. So we'll keep the length as 3. Let's see what happens. If I rewind, undo everything. Oh, click it undo. Yep, run it. We have 89A. Notice it didn't know the 7 existed because the array, the string we passed in was started at 4001. Yeah, there's really a lot of tricks you can do there with Complx. And there's actually another way to call things So right here, we straight up wrote out all the caller code, but in your homework, we only expect it to be the call E. And so if you want to like debug your entire function, you can kind of do a shorthand to do this call E code by just clicking simulate subroutine call. And remember, subroutines, they're really just fancy labels. They're just labels that happen to have calling convention code under it. So Complx can't really tell which one labels you put calling convention code under or not. In this case, we only put it under hex string int. So, but it's going to list all of them. Remember, subroutines is just fancy labels. And we'll put our parameters. Basically what we did over here. X 4001 and 3. And we press OK. It's going to take us to subroutine, and notice that it's pushed our 3 and 4001 for us already. So it basically just did everything we did up here in this caller code, but it just didn't for us already. And it just take us right to this JSR for you. So it might be a faster way to debug a bunch of parameters, especially if you didn't write this boilerplate yet. If I run this whole thing, I expect on top of the stack to have 89A. Perfect. And it doesn't really do anything after returning from the stack, because it doesn't